Hi everyone, in this video we are going to explain the last section of lesson 2, which is analysis of unbalanced three-phase circuits. We have already mentioned what unbalanced circuits are. In unbalanced circuits what we have is that the three loads connected in each of the phases of the three-phase system do not have the same absolute value or the same angle. They are different. They are generic loads which could have any value. So if you remember at the beginning of this lesson, we demonstrated that the difference in potential between the points N and N prime, that is, the difference in potential between the two sides of the neutral conductor, was 0. However, in this case, we are going to calculate the difference in potential, and we are going to see that in this case the difference in potential is not 0. Okay? So, first, this analysis that you have here is for a star-connected system. So, if you have a delta-connected load, then you need to use the delta star equivalence that we have seen in the previous sections and change from a delta connected load to a star connected one. So in that case we will have the following. These will be the expressions for the line currents which in a star connected system coincide with the phase currents. These are the currents that are flowing from the generator and passing through the load. And we are obtaining the current by applying Ohm's law. That is the difference in potential between A and N minus the difference in potential between N and N prime, that is the same as the difference in potential directly between A prime and N prime, which are 2 points, each of them at one side of the load. You can do the same for obtaining IV and IC. Then the current in the neutral conductor will also be, in this situation, the sum of the three line currents that we have expressed before. And besides being this sum, the current in the neutral conductor should be the difference in potential between these 2 points here divided by the impedance of the neutral conductor. So here we have two alternative expressions to obtain the current in the neutral conductor. So then, in this slide, you have the current IA plus the current IB plus the current IC. This sum should be the current in the neutral conductor. That's why it will be the same as the difference in potential between two sides of the neutral conductor divided by its impedance. As you can understand here, you have UN prime N in all the terms. So, if you want, you can separate these differences into two fractions, and after that you can solve for UN prime N. And you can isolate all the terms with UN prime N at one side of the equation. So in that situation you will have something like this. You will have this term, which is difference in potential between A and N divided by the impedance of the first load, this other term, and this other term, and in the other side you will have this that you have extracted because it was in all the terms, and multiplied by 1 divided by the impedance of each of the three loads connected to the phases plus 1 divided to the impedance of the neutral conductor. If you solve for this difference in potential between the two sides of the neutral conductor, there you will have this expression. And here 1 divided by the impedance is the same as what we call the admittance. So here we have substituted 1 divided by impedance 1 by admittance 1. Okay? So you will get to this expression here. That means that if you know the values of the impedances of the loads, you can get all the values of the admittances, and then you should know also the value of this phase voltages here between one phase and the neutral conductor. And then you can get the difference in potential between the two sides of the neutral, which is also called the voltage displacement, okay, or the displacement voltage as you have here. So initially this displacement voltage is not going to be zero anymore when the system is not balanced. With that information, we could now solve example 6, in which you have an unbalanced three-phase load which is connected in a star.
Hi everyone, we are in example 6 of lesson 2. In this example, we have an unbalanced load. That means that the three impedances connected in this three-phase system in each of the phase conductors, they have a different value. And they ask the value of the line currents IA, IB and IC and the value of the current which is returning through the neutral conductor. So, first of all, we need to consider one phasor as reference phasor. And they say that we should consider phase voltage A as reference phasor. That means that phase voltage A has an angle of 0 degrees, while phase voltage B has an angle of minus 120 volts, while UC has an angle of 120 volts. So in this example, we need to obtain each of the currents, and we are going to do so by applying Ohm's law to each of the impedances. But first, we will need to express the impedances in polar notation. So then, we are going to obtain the absolute value of the first impedance, which is approximately 11.18 ohms, and the angle of the first impedance, which is arctangent of 5 divided by 10, 26.57. So then, if we apply Ohm's law, we will have the phase voltage UA divided by the impedance. That is because we have this impedance connected in a star, and the difference in potential between these 2 points coincides with voltage UA, phase voltage UA. So that is 230 volts divided by 11.18, 26.57 ohms, which gives the current of 20.57 minus 26.57 amps. So that is line current A. For obtaining line current B, first we need to express this impedance in polar notation. The absolute value is the same as in impedance A, but the angle is different. In this case, we have arctangent of minus 5 divided by 10, which gives the same angle as before, but now negative. Line current B will be phase voltage V divided by impedance B. That is 230 minus 120 volts divided by 11.18 minus 26.57 ohms. Now we need to do the same with the third impedance. The third impedance expressed in polar notation would be 10 ohms. So line current C would be, and the result is, as you have seen in this example, when the load is not balanced, the different line currents do not have the same absolute value here, okay? These two currents have the same absolute value only because the absolute value of these two impedances were equal. But here you have a different value. So in this situation, they also ask the value of the current, the line current, which returns through the neutral conductor. This current is going to have a value equal to the sum of the three line currents. But now we are going to see that this sum is not going to be zero, because this sum is only zero when the load is balanced. And here, as you can see, if we sum these three currents, these three line currents, we will get to approximately 11.33 minus 60 degrees. in amps. So, remember, the current in the neutral will only be 0 when the load is balanced.